Okay, so next lecture time. At this point, you guys should all be almost done with working through the homeworks for two-dimensional kinematics. Remember, those are due in a couple of days here, on Wednesday. Also, I have written the exam. So there will be an exam on Friday. There's not going to be a lecture. I'll send out an email about this again too. But there's not going to be a lecture. The exam will go live on Friday morning at 8, and you're going to have until Saturday at midnight to complete it. I have changed the parameters in the system a little bit, so you get one opportunity to answer the question. So take your time. It is worth maybe printing the answers or printing the questions and then work on them before you go into the system to submit your answers. Also, there are going to be a couple of questions on the exam that are going to ask you to show your work. And the way it wants you to do that is you're going to have a button to attach a file. So each of those questions, you're going to have to get some notebook paper or something and write some things down, showing me some equations or drawing diagrams or something, and post those individually to each question. Don't give me just one file with all the answers. You need to do them individually, attached to the question, so I know which work goes with which question. It'll be pretty easy. Like I said, I'm giving you basically 2 days to do this thing because you have the luxury of doing this as an online class and being at home and being able to refer back to notes and books and everything to look things up. So you should be okay. All of the questions that I put on the thing come directly from the homeworks. So there's nothing on there you have not seen, especially if you've been doing the homeworks. So having said that, I want you to continue working on that, and we're going to start into chapter 4 today. Chapter 4 will not be on this next exam. The Friday exam is only going to cover unit conversions, 1D motion, and 2D motion. Everything we've done up to this point. This block, starting with chapter 4, and probably for the next 3 or 4 chapters, will comprise exam 2. So we're going to kind of shift gears a little bit. We have been talking about kinematics at this point in motion from the very basic standpoint of velocities, displacements, and how those things change over time. What we're going to start doing now is we're going to start describing force or movement with a little more detail. And we're going to get to this idea of force. Force is a core concept in physics. In fact, we're going to have a unit for measuring force that's called the Newton. And that is not a coincidence. It's actually named for Isaac Newton. So Newton came up with 3 laws, we can call them laws, that govern motion. The first, second, and third law, and we're going to go through these and talk about what they mean. But in general, if you have something like, if you can imagine this dolphin here jumping out of the water at SeaWorld or something, you know that it's going to kind of follow this curved path. There's going to be some way that we can measure, and we've already done a little bit of this with 2D motion. If you model the dolphin as a spherical cow in a vacuum, then we know how things are going to move, and we can model them. And so Newton's laws give us a little bit better way to describe what's going on here. Before I get into that, though, I want to show you something. Something that you may not have noticed. When you've been doing the homework problems for the 1-dimensional and 2-dimensional motion, the only thing we've known about our projectile is something about velocity and position. We don't know anything about how big it is. We don't know anything about its mass. But we've been calculating all these things with like range equations and finding the range of something based on the time of flight. That seems weird when you think about it, because that means according to those models, we could easily be modeling, for example, the volcano problem. We never did anything mathematically to say that this was a boulder being shot out of a volcano at some velocity. We've always modeled a spherical cow. There's no reason that thing couldn't have been a feather. And our math tells us that it doesn't matter if it's a giant volcanic boulder or a feather, that those times of flight are going to be the same. And you might say, well, that doesn't make any sense, because I've seen feathers and I've seen bowling balls fall, this kind of thing. Well, I want to show you a couple of things here. Here is a video that was shot on Apollo 12. This is one of the astronauts on the moon, and what he's done is he has a hammer and a feather. The video quality of this is somewhat poor because this was 1970. Second. So here we have our astronaut, and he's got a feather and a hammer. And what he's going to do, standing on the surface of the moon, is he's going to release the hammer and the feather together, and they're going to hit the ground at the same time, proving what I just said, that this time of flight characteristic doesn't have anything to do with mass. So think about what's going on the moon. The moon has no atmosphere, right? You didn't know that. That's true. It has no atmosphere. And oh, look, there they go. The hammer and the feather hit the ground at the same time. It looks really weird. Remember, the moon does not have an atmosphere, and the acceleration due to gravity on the moon is much, much lower. It's about 1/6 of what it is on Earth. Now, there are conspiracy theorists out there that will tell you this was all fake. This was all done on a soundstage on Earth. And that, oh, this is not going to work the same way on Earth. Well, I have an answer to that too. Here's a second video. This is a guy called Brian Cox, who's a physicist in the UK. Really smart dude. And what he's done here is he's gone to a vacuum chamber. I don't know where this is, but it's a giant vacuum chamber that's the size of my classroom. And he has rigged a bowling ball and a feather in some contraption at the ceiling of this vacuum chamber, sucked all the air out of the chamber and released them. And what we should see is the bowling ball and the feather hit the ground at the same time. Now, this is on Earth, right? Again, I don't know exactly where this facility is. It doesn't really matter. So there's Dr. Cox. So here's our bowling ball and our feather in slow motion, just to show that there's no camera trickery. Falling at exactly the same rate. And they hit the ground at the same rate.
Right. Did that happen?
Do what?
A feather and a ball fall at the same time?
Yep.
That's-
So, like I said, it looks weird, right? So
Yeah.
why is that? Let's examine our equations of motion again. If you have your notes in front of you, if you remember doing the homework problems, for example, if we look at just objects in free fall and we want to know the distance and the time, remember what that equation looks like. If we use the y-axis, it looks like y equals y naught plus at, where y is final position, y naught is initial position, a is acceleration, and t is the time. Nothing in there has anything to do with mass. It only has to do with position and acceleration. So it appears that these two things are falling at the same rate, and they are. The problem is that when we see things in our normal daily lives, there are lots and lots more forces acting on that than we normally think about and can see. The big one is air resistance. And that's why in a normal environment, the hammer and the feather, or the bowling ball and the feather, would seemingly fall at different rates. Because when you have air, the air is going to act more easily on the feather than it will the bowling ball. And that has to do with densities that we'll get to in a little while. And so you have another force, and that's—
How can I help?
Say again? What'd you say? So this is a way that we start thinking about Newton's laws, that there are other forces. Now, we're used to thinking about gravity as a force. A lot of times you'll talk about the force of gravity. Remember, and kind of think about this, nothing we have talked about up to this point has anything to do with force. It's all been about acceleration. Our acceleration, or our G, is the acceleration due to gravity, but it is not a force. And we're going to get into those differences here in this chapter. Now, a lot of this work Newton worked on in the 1600s. He published this work called Principia Mathematica in 1687. This is the first time that these laws of motion were laid out. The interesting thing about Principia Mathematica— yeah, I know my mic is on. Oh, you're talking to somebody else.
Okay, I was trying to tell somebody who had the baby's mics on. I thought that was the person.
Oh, I see. Hold on. I think I can mute them. There we go. Okay. Sorry about that. So the interesting thing about Principia Mathematica here is not only does it lay out Newton's laws of motion, this is also the origins of calculus. Newton invented the mathematics of calculus in order to describe motion, in order to describe the physics that we're going to talk about. We did not, up to this point, have a good mathematical system for predicting this motion. And this is what physicists are predominantly concerned with, is predicting what motion and energy and systems and everything are going to do over time or given some variable. So Principia Mathematica is sort of the physicist's Bible. So here's the kind of thing that we want to look at. And this is the way that most of the problems in this chapter are going to work. We need to start thinking in terms of vectors. Remember, I gave you a little brief introduction to vectors before when we were talking about X and Y components of things. Those are just vectors. But now, instead of our vectors looking like a distance or a velocity, now they're going to look like a force. The first thing that you should notice in this diagram is this right triangle shape here. Anytime you see right triangle shapes, you need to start thinking about trig functions. We're going to use the same trig functions just like we did when we calculated X and Y components of velocities. We're going to do the same thing with force. So in this example, this free body diagram, I want you to pay attention to a couple of tricky little things here. So what we've done is we have a couple of ice skaters, okay? We have one in the center, one at the back, one at the side. We're saying these are ice skaters so that we can say there is no friction between them and the surface. We're going to learn later in this chapter how to account for that friction. It's really not all that difficult. But for now, since we only have to worry about one force, we don't have to worry about a force of friction. Nothing is taking energy out of the system. In order to do this problem, what we want to know is if we have this figure skater in the center and the person in the back and the person on the side each push that skater with some force. So this person over here, we're just going to say they apply F1 or force 1. Down here is F2. This is force 2. Nothing says that those two forces have to be equal. If you want to think about numbers here, just kind of help you wrap your head around this, think about the amount of force it would require. How hard would you have to push if you had, say, I don't know, a 10-pound bowling ball or a 10-pound brick, let's say, so it's not spherical and you don't have to worry about rolling. If you have a 10-pound brick next to, say, a penny sitting flat on a table, and think about how hard you would need to push in order to make those things move. That is a force. So in order to make the bowling ball move, you'd have to push it much harder, or the brick, you'd have to push it much harder than you would have to push the penny. So the magnitude of the force on the brick would be much greater than the magnitude of the force on the penny. So here we have two people pushing on this person in the center. Again, we can treat this as spherical cow in a vacuum, except later on, you're going to see that we're going to actually worry about mass. So when both of these people push the person in the center with some force, we would like to know what direction that person moves, and we would like to know how fast they move in that direction. And you can kind of envision that pretty easily. Well, the way we're going to find that out mathematically is by treating these as vectors. So notice where I have my people positioned. Now, the thing about forces is we don't really care where the right angle is here. We're just going to make sure that we have a triangle with a right angle. So what we want is the total force. So what we do, if you notice in this triangle here, we have F1 as a dashed line. Notice that it matches what F1 is here with the solid line. And we take F2 and we draw the tail, or at least or the starting point of the F2 vector, and we line it up with the head, just the direction of motion of the first vector. Make them perpendicular. There's our right angle. And then if we draw a line from the tail of the first vector to the head of the second vector, that is what's called our resultant vector. In this case, that is our total force. So we have some amount of force applied in the positive y direction, and we have some amount of force applied in the positive x direction. This is going to result in some force that is in whatever that angular direction is. Now, the magnitude of those forces, how hard we push from either the back or the side, is going to determine the angle of that resultant vector. We already know how to do that. It's exactly the same thing that we were doing in the last chapter. We know how to use trig to find the angle between the two. If we were given the angle between the two and one of those other forces, we could find the magnitude of the other two forces. So you can see how it's exactly the same skill. The other thing that we're going to do here, in order to make this really, really simple, is we are going to learn and we are going to start doing things like free body diagrams. That's what this is. So a free body diagram, notice, is an origin. We pick whatever origin we want. Then we pick a direction, positive and negative. And then we draw our forces with those origins. What we're going to get here is going to be called a free body diagram. This is going to help you tremendously when you go to do problems. This is the way you're going to set things up. You're going to notice if we draw the vectors this way, like in pink here, we put our two source vectors head to tail. And we got this result. Here we put them tail to tail. If you do that, you know your resultant vector is going to start with the tail wherever those two tails come together. So again, at the origin. And our resultant vector is going to be, in this case, some positive in the F1 direction and some positive in the X2 direction. So that gives us the same resultant vector. It doesn't really matter how we've set this up. Doing it this way with the free body diagram, tail to tail, is really going to be a whole lot easier for you. And as we start doing problems, I'm going to show you this. Remember, this portion here is, like I've done before, without trying to do problems or anything right now. I'm trying to get you to understand the concept of what we're going to see. And then we're going to come back and re-attack this and actually do problems. Other things you can do with this. It doesn't have to be the figure skater problem. This can be a spring problem. So here I have a spring. It's attached to some rigid surface. The spring has some length X. I apply a force to the spring. In this case, we're going to pull the spring with this handle. So what we've done is we have applied some force. Now the spring wants to go back to its rest position. So we have a restorative force in the opposite direction that we're pulling. Because as soon as we let go of that handle, we're no longer applying the force to pull the spring back. The only force that's going to exist is that restorative force in the spring. So what we need to know here is that we have a distance that was the original length of the spring, and then we displace the spring. We have some delta X is our displacement, and we have some restorative force. We can use this information, and we'll see this later on. We'll do this kind of problem. This is called Hooke's law, by the way, where we can find this restorative force on the spring. In order to do this problem, we're going to need something called the spring constant, and we'll get to in a little while. The spring constant is just kind of a measure of how stiff the spring is. So if you think about the spring in a car suspension system, the shocks, those are going to be pretty heavy, thick springs, and they tend to not want to move a whole lot, as opposed to a spring in, I don't know, a watch or slinky or something. That's just a spring. That's going to have a very small spring constant. And so it's more readily going to move around. That's all spring constant means. Again, when we start doing problems with this, we'll get to it. This is kind of a common example that we're going to be doing. We have some kid in a wagon, and we are applying a force, this F1, to the right on the wagon. And we would like to know something about maybe this A, which is acceleration. We'd like to know how quickly we're changing the velocity of the kid in the wagon. Well, if you look at this diagram, we've labeled a bunch of things. We've labeled this A, that is our direction of acceleration. We've labeled F1 and F2 because we have two people pushing the wagon. We have F1 is going to be less than F2, but they're both in the same direction. Then notice here we have something called weight, that's W. And we have something called N, that's our normal force. These are all going to be forces, with the exception of A, acceleration. And, oh, look here, there's this small f. It's in the opposite direction. That is friction. Friction is going to want to stop moving things. So when we go to do our free body diagram, we pick some origin. In this case, we'll say the origin is right here where we're pushing, back of the cart. That's where I'm going to set my 0. And then we go label all these things. We say, aha, I have a normal force that's acting upwards. We'll talk more in detail about what normal force is in a bit. Just for right now, it is a force that always opposes weight. So we have a normal force that's going to act in the positive y direction. We're going to have a weight acts in the negative y direction, which should tell you that the weight has something to do with acceleration. We have a force due to friction that's acting to the left. Notice it's opposing motion. And in the forward direction, or the positive x direction, whatever we want to call it, we have two forces, F2 and F1. It doesn't matter which one of these you put first, because we're just going to go head to tail with those. They're going to add. This kind of makes sense, right? The more people you get pushing this, the more force you add behind that wagon, the faster it's going to go. Notice that weight and normal force are not going to change unless we put more people in the wagon. Then that's going to change. Friction is not going to change as long as we're on the same surface. Now, if we go from concrete to ice to sand, we're going to have a couple of friction force transitions. Don't worry about that just yet. We'll get there. And here we have basically the same thing, right? Except we only have one force pushing the wagon, but it's somebody that's much stronger. There's only one force vector and it's bigger, but everything else gets labeled exactly the same. Not a big deal. This is how you do free body diagrams. Notice that these free body diagrams that we've drawn here are much, much simpler and much, much easier to read than this picture. The free body diagram is your friend. This is where the physics is going to happen. And this is what's going to allow us to more easily make calculations about what's happening in a system. So just another example. Here we have some dude. He has a basketball. And that basketball has some mass. M1, let's call it. He applies a force. Let's assume in this case, both forces are the same. So F is some amount of force. It's the same. Maybe it's 10 pounds, maybe it's a joule, maybe whatever it is. It doesn't matter. It's the same force. If we apply that amount of force to a basketball, the basketball is going to accelerate pretty quickly in that direction. So imagine you have a basketball and you just push it like that. Don't try to yeet the thing through the wall. That's a word you guys use, right? We are just going to kind of normally throw the basketball. Think about that amount of force. And then think about standing behind a car and trying to push a car with that same amount of force. You're not going to accelerate that car very much. The basketball, you will. So this implies that the amount of force that we need in order to accelerate something is going to be a function of the mass of that object. Notice the velocity here is not even in this diagram. What we've been talking about before has been velocity. Velocities are not in this diagram at all. I don't know anything about that. But I can derive it if I can find acceleration. Because remember, acceleration is just a change in velocity over time. Well, if we know an acceleration and we know a time, we can find a velocity, which could then be used to do our projectile motion problems. So the way we're going to do this in this kind of problem here is we're going to say, well, I want the net force is 51 newtons to the right. And I want to know what the rate the lawnmower accelerates at. Well, I'm going to show you how to do this. See if I can find how to add. There we go, text box here. So what we're going to need to do this is we need to know something about the relationship between the force and the acceleration. Well, we know that the force applied to something has got to be in some way proportional to the mass. In other words, the bigger the mass, the more force you need. And the more force we apply, the faster it's going to accelerate. So force and acceleration are proportional as well. Notice how we did this. We came up with this kind of equation, this F equals ma. Force is mass times acceleration. And we did that just by kind of thinking about what's happening, just through our observations. This is exactly the same thing that Newton did. In fact, this equation you might have seen before. This is a very, very simplified version of Newton's second law of motion. Newton's second law of motion says that the force required to, the force applied to an object is going to be directly proportional to its mass and acceleration. Has to be. We're going to use this information and this idea of how this formula works to solve this problem. One more thing, though. Notice that it said the net force on the lawnmower is 51 N. That's an N. That's a Newton. Well, I'm going to show you what a Newton is real quick. A Newton is the measurement of force. So we're going to do some dimensional analysis. A Newton is a measurement of force. That's just what we're going to call it for now. Well, why are we going to call it a Newton? Well, if we try to figure out what this means, mass is typically measured in kilograms. Acceleration is typically measured in meters per second squared. So combining these two together, you get something that looks like kilogram meters per second squared. There's nothing wrong with that. I don't have a word for kilogram meter per second squared. Well, neither did Isaac Newton. So you know what he did? He said, I am Isaac Newton. And I literally wrote the book on physics and mathematics. I think it is only fair that I name a unit after myself. So the unit of kilogram meters per second squared is called a Newton. Newton is what we're going to work with when we talk about forces. So don't expect to see forces show up in terms of kilograms or meters per second. Expect forces to show up in newtons. And remember, a Newton is a kilogram meter per second squared. This should make you think, aha, that's why we spent so much time working on unit conversions in chapter 1. Because we need to know how to do that. So in this case, what we're going to do is we know, we go back to our checklist, right? Have solved physics problems. We've drawn a picture of this. We have some known values. We know the net force on the lawnmower is 51 newtons. We want to know what rate the lawnmower accelerates to the right. We need to know a rate of acceleration. So we're just going to do some algebra. we're going to rearrange the equation and solve for acceleration. That's what we're trying to find, right? So acceleration in this case should be pretty easy to discern, is just force per unit mass. Well, let's say, for example, that our lawnmower weighs 10 kilograms. We already know the force. So that would mean acceleration is going to be 51 newtons divided by 10 kilograms, which should equal 5.1 meters per second squared. That's how fast the lawnmower is going to accelerate. Let's prove this is true through some dimensional analysis. We know acceleration is force per mass. We know that force is kilogram meters per second squared. We know mass is in kilograms. So kilogram meter per second squared total that divided by kilograms. Look what happens. The kilograms cancel because you got kilograms on the top, kilograms on the bottom, and that works out to be meters per second squared, which is the appropriate unit for acceleration, which is exactly what we want. So we know our math works. That's how we're going to do Newton law problems. Almost everything you do is going to come down to F equals ma. It may not look like it at first, but that's how it's going to work. Here is another kind of typical free body diagram. So here we have some kind of rocket sled, and we put a whole bunch of rockets on the back of it. If you can make a thing go really fast with one rocket, then the way to make it go faster is put even more rockets on it. So that's what we've done here. We have some car that has some mass, and we have some force. We're going to label it T here because that's going to be our thrust. So thrust is a kind of force, right? It's a measurement of force. That's all we're doing. Well, it looks like we have 4 motors here. So we're going to say that we have some friction here. We have some weight. We have some normal force. We're going to accelerate this thing at some acceleration A. Draw a free body diagram. Label all your forces from the origin somewhere that makes sense. And look what we get. We get our normal force and our weight force are going to cancel each other. We're going to have our friction force, and we're going to have the sum of all 4 thrust forces. This is a good time to take a look at what that normal force is. The normal force is the opposite of mass times gravity. That's a little strange, but think about this. What is weight? Weight is nothing more than a force. We know that force is mass times acceleration. Since force is mass times acceleration, if we measure mass as just mass, right? We don't really care what units we use. So mass is just going to be mass. The acceleration we have here is the acceleration due to gravity. So just G. Now, where the hell did my negative sign go? Well, I've done this intentionally. I'm doing this generically. Force is mass times acceleration. In all cases, it doesn't matter at this point what the directions are. Remember, a negative sign is just direction. So whatever direction I choose to look at the force is going to be dependent on the direction I choose to look at the acceleration. So our acceleration here is the acceleration due to gravity on Earth. We generally think of that as being the down direction, but it doesn't have to be. But the normal force then, so that's mass times gravity, that is weight. That's what you're measuring when you step on the scale. And you might be wondering, well, why in the hell does my scale not show me my weight in newtons and it shows me my weight in pounds? Well, that is because we use freedom units. If you look at the units that we tend to use in the US, weight is not kilogram meter per second squared. We don't use the kilogram as a measure of mass. In fact, we use a unit of mass that you have probably never heard of before because we rarely ever talk about mass in this context. In the imperial system, the unit of mass is something called the slug. The acceleration due to gravity, again, we don't use meters, we use feet. So we have feet per second squared for acceleration instead of meters per second squared. So the pound, not the British unit of currency, but the measure of mass that we use in the imperial system, or weight we use in the imperial system, is really something that looks like slug feet per second squared. What's a slug foot? I'm not a biologist, couldn't tell you. You can see why, as scientists, we like to use metric system, because it's kind of easy to understand what a kilogram is, but it's really hard to describe what a slug is. And it keeps everything nice and simple, and we don't have to do a lot of conversions. Well, in this case, our weight is mass times acceleration due to gravity. As long as we use mass in kilograms and we use acceleration due to gravity in meters per second squared, there is no problem. We just know that the normal force is the opposite of weight. So that's where that negative comes from. How do I know that it's opposite? That's Newton's third law of motion. Newton's third law of motion says that for every action, there's an equal and opposite reaction. It's probably the way you've heard it phrased. That's not entirely accurate, but it's a good enough way to start. What it really means is that if there are contact forces, in other words, if something is contacting something else, this rocket is contacting the ground, the rocket is going to push down on the ground, right? Because it has weight. The ground has to push back. Well, since the rocket doesn't fall through the ground, and since the ground does not push the rocket up, off the ground, right? Doesn't launch it. Then those two forces must be equal. So that means that in this case, N and W have equal magnitudes, but opposite directions. So they cancel each other out. Most of the time, if we are doing a problem like this, where we have just kind of a flat plane, we're not going to have to worry about the normal force because it's going to cancel directly with the weight. However, probably Wednesday, we're going to start talking about problems where that's not true, that we're not on a level surface, that we're going to be on some incline. Then we're going to have to start worrying about the normal force a little bit. I'll show you one more slide on this, and then we'll quit. Again, same thing. Different system. Swimmer underneath the water. It's going to push off the wall and accelerate forward. So we just draw our free body diagram. we pick some convenient point of origin. In this case, probably the wall, right? Where her feet contact the wall. We're going to call that the origin. Well, we know that she has some weight, W. We're going to need to know about the normal force here, right? She's going to push on the wall. So she's trying to move the wall back that way. But that means, because of Newton's third law, we have an equal and opposite force. That's going to be that normal force, right? That's the force of the wall on her feet. Doesn't matter, right? As long as we keep our direction signs same. And the last thing here is this BF. That's the buoyant force. This has to do with why you float or sink. If buoyancy is neutral, you're not going to go anywhere. If buoyancy is positive, generally you're going to float. If buoyancy is negative, you're generally going to sink. So if we're going to assume neutrally buoyant, you're just going to stay kind of at the same depth in the water, then buoyant force and weight are going to cancel each other out. We've still got this force propelling us forward because we know we're not going to move the wall. So all that force is going to go into our swimmer. And so now we know something about a force, right? Well, if we knew something about the mass of the swimmer, then we could determine something about the acceleration of the swimmer. And if we know something about the acceleration of the swimmer, we know something about the velocity of the swimmer. Once we start getting into friction, we can think about what force does the water apply on her, because it's going to slow her down, right? So that's going to be our frictional force. This is exactly the same way air resistance works. Air resistance just applies a frictional force. And we have to kind of think about that. So I think that's where I'm going to stop for today with the lecture. Again, I just wanted you to start thinking about how to do this. And in the next lecture, we're going to start solving problems like this, where we have some mass on an incline and it's going to be moving. We know the angle of the incline, and we're going to have to start solving about some things for forces. So that's where we're going to go. We might have any questions before we are done here. Nope. All right, then I will see you guys on Wednesday. Remember, if you have questions, email me or come by.